This tutorial is about how we use our angles in our free body diagrams. So when you have a diagram with forces and they could be going in all different directions, let's just call them for now A, B, C, and D. What we do is we bring in the Cartesian coordinate system so that we can use sine and cosine to get the components of the vectors that aren't perpendicular, right? So usually we make the y-axis go vertical and the x-axis go horizontal like they usually are, right? Most of the time we do that. Now, once you have the axes in there, then you can see the vectors that aren't flat on the axes. B is flat on the y-axis, D is flat on the y-axis, but the way I've drawn it, vector A here is not flat, and vector C is also slantways. So you identify your slantways vectors, and a vector like this red vector here is going to the right and up. So some of the vector is going sideways and some of it is going vertically. So you need to be able to resolve it into its components, which means figure out how much is going in the x direction and how much is going in the y direction. And to do that, we use sine and cosine. And to do the trick that we normally do, we always need to find the angle between the slantways vector and the nearest version of the x-axis. So for this A vector, the angle is here. Let's call that angle theta. All right? And so we have two components of the vector A. There's this sideways component that goes out to here, and this is going to be A cosine theta. And then there's the vertical component that goes this way, and that's A sine theta. I should have said capital A sine theta. And we're going to put it into our equations like that. And let's say that we also needed to do this vector over here, vector C. To do that, we need to find the angle between this slantways vector and the nearest version of the x-axis. We don't have to go all the way around this way. We don't have to go all the way around that way. We can do the closest one, because this isn't math class and we don't always have to measure from the positive x-axis. So let's call this angle here alpha. Right? So for this vector, we're going to have the x component is going to go this way, and that's going to be C cosine alpha, and the y component is this way, C sine alpha. Right? So when we go to do the equations, it's not that hard, right? The x equation, we're going to include every vector that was flat on the x-axis, so there weren't any. And then we're also going to include the x components of the slantways vectors. So my first slantways vector was the red one, A. So I'm going to put A cosine theta. It's cosine because this is the x equation. It's A because that's the name of the vector. And it's theta because that's the angle between that vector and the x-axis. It's positive because it's going to the right. Then the other one is this purple one over here. So I'm going to say C, cosine again because it's still the x equation, alpha because that's what the correct angle is there. But this one's going to be negative because this one goes to the left. And then that's going to be equal to MA minus MA or 0 depending on what's happening. In the y equation, I'm going to include these two vectors that are flat on the y-axis. So B is up, so that's positive, and it doesn't get a cosine or a sine because it's flat on the axis. D is downward, so that's negative. It also doesn't get a sine or a cosine because it's flat on the axis. And then we need to do the y components of the red and the purple vectors. So the red vector A goes in here, and we're going to use sine because this is the y equation. We're going to use theta because that's the angle associated with that vector. And it's going to be positive, this one, because this vector goes up. So it's plus a sine theta. And there's a sort of a pattern to it, because if you have a cosine theta in one equation, you know you're going to have a sine theta in the other equation. Now I go and do the c one. Well, I see that I had c cosine alpha before, so it's going to be c sine alpha. And now I just have to think about whether that should be positive or negative. Well, this purple vector is going down, so that's negative. Remember, in the x equation, we only concern ourselves with left and right, and in the y equation, we only concern ourselves with up and down. So that's the total amount of force happening in the y direction, and that's going to be equal to ma or minus ma or whatever it is. All right? Now, this would be the type of situation you'd have if you had a bunch of ropes pulling on something, or just forces were being applied at angles for some reason. Now, it's different when you have a object sitting on a hill, right? So if we have an inclined plane, which is the fancy physics word for a hill, we have a hill that has an angle of incline of theta, and you have an object sitting on the hill, then a lot of things are going to be slantways, right? When we go to draw this free body diagram, we're going to have mg pointing downward, because mg always goes down regardless of whether it's a hill or flat or what's happening. Mg always goes down. Then the normal force is always going to be perpendicular to the surface, and the surface is at an angle, and so the normal force has to be perpendicular to that. So the normal force is going to look like this. Normal force. And then maybe we have friction here. Friction always goes parallel to the surface and away from the possible direction of motion. So if this was something that was going to slide down, then the friction will go up the hill. So we have a free body diagram that looks like that. Now, when we go to bring our axes in to do the components for the equations, it's always a smart idea to put, well, almost always a smart idea to put the y-axis on top of the normal force. Obviously, we're going to put the origin of the axes on the center of mass, but putting the y-axis through the normal force is a good idea, because if there's going to be any motion, then the motion is all going to go on the x-axis. Because when something's sitting on a surface, it's not going to move this way. It's only going to move that way. And keeping the motion on one of the axes is a really smart idea, because it makes it much less complicated later. So now that we have our axes in, remember, y-axis on the normal force. I can't think of any time when that would be a really stupid idea, but sometimes it's equally good to do it the other way. But if you want to make a rule to always put the y-axis on the normal force, you'll do really well. So we're going to put we put the y-axis on the normal force, and we're looking at our vectors, and we see that the normal force vector is flat on an axis. That's easy. The friction vector is flat on an axis. That one's easy. The only hard one is the mg. So when we have a vector that's not flat on an axis, then we need to find the angle between that vector and the x-axis, always the x-axis. So we see that that angle is here. Now we need to figure out from geometry what angle that is. And what I want to try to convince you of is that this angle is this angle up here, right? And if you're not sure you believe that, look what happens if I draw the free body diagram right here instead of over there. So I have normal force like this, right? I have friction along the surface, and then I have mg going down. See how the angle between the x-axis and mg is right here? That's that angle, right? Or even if you look in this triangle here, you can see, because this is right angle here, right angle there, right? You can see from the geometry that this angle in here is 90 minus theta. So we are always going to be using 90 minus theta in our free body diagrams of an inclined plane, right? Not in ropes pulling, but just when there's an inclined plane, when it's on a slant. On a slant means use the complement. Right? So then we go to write our equations, and they're not so hard. In the x equation, we have the frictional force, which is moving. If you tip your head to the side, you'll see the frictional force is moving to the left. So that's minus F. No angle because it's flat on the axis. Normal force doesn't go in this equation because it's on the other axis. And then we have the slantways one, which is mg. We're going to say cosine because this is the x equation. And we're going to do 90 minus theta because that's the angle that we identified right there. Now, this one is, if you tip your head to the right, you see this is the to the right direction. So this is going to be plus. And that'll be equal to whatever it equals, ma minus ma, or 0. For the y equation, we have the normal force. It's positive because it's going up. And then we have the y component of mg, which we know is going to be mg sine 90 minus theta, right? Because sine because it's y, 90 minus theta because that's the angle that's associated with that. Notice it's always the same angle in both equations. And this one's negative because it's going downward. That's the down direction, right? And that's going to be equal to 0. Because whenever there's a normal force, then it has to be equal to 0. That's the normal force's job.